But once you get it going, it seems to work
This is
pretty
great,
well.
it just emails it in, so, all right,
Yeah.
that's rolling, so you can go ahead and introduce yourself.
All right, and then I have you guys watching there, so let's, yeah, we'll turn these off so they show up better. And, all right, I am Steve Running, Regents Professor of Ecology over at the Main campus. And I'm here to give a lecture for Brad, and in this way, this is a biorenewables class, and so what I decided to do is give you the same lecture that I gave as a public talk over in the World Forestry Institute in Portland only about 2 months ago. So I thought that was pretty relevant to this group. This maybe has a little bit more global carbon cycle theory than you might want, but too bad. It's an important part of understanding this overall issue. And so I think it actually it is a good thing for you to get a little background on. And then we'll zoom into the bioenergy part of it as we work our way down through the topic. So let's see. Now that should be launching us. Oh, wait, now didn't it? Ha! Oh wait, now this is up on that screen. So this keyboard is running the big monitor.
Yep.
All right, that's fine. Yeah. Okay, so yeah, of course, for this World Forestry Institute, it's an international organization. They were very interested in the role of forest and climate change more generally, not only bioenergy, but I saw the bioenergy aspect of it as a real important part of what I wanted them to know about. And so there's a fair bit of that. Now let's see. So there we go. Now I'd have to say when I was in graduate school, none of us ever imagined doing policy relevant research, having journalists interview you, having stuff in the newspaper, and then having people write nasty things back at you, which happened just yesterday. And so I find that in today's world, the role of us in science is a lot different than what we thought. I'm a forestry graduate, actually. My BS, MS are from Oregon State and my PhD from Colorado State. So I started this was my master's thesis work, measuring drought stress in trees. What I've morphed into in global scale science, now this is interesting. The main line doesn't show on this monitor. Isn't this always a surprise? I would hope most all of you have heard of the Keeling curve. It's the measure of CO2 in Mauna Loa that was started in 1957 by Dave Keeling. That's him riding up the Snowball chairlift with me a number of years back. And basically it illustrates what the graph shows there, that CO2 in the atmosphere is particularly in the last half century just taken a shot straight up. You know, when Dave was alive, and he died here in Missoula, the most famous earth scientist on earth, he died in Missoula Hospital, and I don't think it even made the papers here. And yet he was by far the most famous earth scientist around. Even he didn't really think the CO2 increase was going to develop fast enough that it would trigger the kind of global warming that we now are seeing. And so he made this quote in 1968, and he really thought, you know, somewhere in the next 100 years or so, we're going to have to start paying attention but in no way did he think, by this early date, we'd be in the pickle we're in now. Now this is a main topic in things like the State of the Union address, where Obama gave a very clear statement of the state of affairs. The Senate actually has voted that it's real, even though people don't know that. Of course, the very next vote, 5 minutes later, was are humans causing it? And then the vote was something like 48-52. And so, but even these politicians that don't want to talk about it one bit understand quietly that it's real, and it's a pretty sorry state of affairs of their leadership that they're not even willing to talk about it. I'm not Catholic, but man, the Pope really did us a good favor last summer, because that encyclical, I'll bet none of you have ever read a papal encyclical before. That isn't what I read very often. I read this. You wouldn't believe the technical language. Well, in fact, there's a quote out of it. That's out of a papal encyclical? Are you kidding me? So he has really come out that this is real. The religious community has to be part of the solution, and he wants to get people woke up. What's been very heartening just in the last couple of months is now the big corporate titans for the first time are really weighing in. And this wasn't true 3-4 years ago. That title says it all there from November 29th. More than 20 other billionaires, I can't remember how much money they put on the table, but it was lots of billions, and it's their own money too. This isn't point in government money. This is their own money out of their own foundations. So, and it's actually an awful lot of corporations. What they're doing is not getting into the climate political wars. They're simply quietly looking at their own business and saying, we know how the future is unfolding. How are we going to be ready to not only stay in business, but maybe, depending on what we do, maybe doing better than our competitors because we paid attention sooner than they did. And so an awful lot of companies that you recognize have signed this document, the greatest economic crisis and opportunity of the century. And so it's interesting for me as a climate scientist to watch just in the last 2 years this transition. And they don't even bother talking climate politics. They just walk right past that and get right into how are things affecting what we do and how can we do what we do position better. So this is where we should have been 10 years ago. But at least we're finally getting there everywhere except Congress. All right, some hard facts. And this comes from a thing called the Global Carbon Project, which is scientists all around the world. And they compile all these statistics all over the world. And this is what CO2 emissions have done worldwide since 1990. And a couple things there worth noting. First is how starting just past 2000 is when it really took a leap forward. Second is, you'll notice in 2009 emissions went down for a year. That was the big economic downturn. But more interesting is this last year, for really for the first time, it went down without an economic downturn. So this is our first evidence that we actually could slow carbon emissions if we want to without wrecking the global economy, which is what a lot of the argument is. Oh, we can't do this. The economy will collapse. And now we're starting to see evidence that that doesn't necessarily have to be true one bit. Here's what it all comes from. It's interesting that things really started ratcheting up in 1950, which is the year I was born. So all of this has unfolded in my lifetime. And you'll see it's all burning fossil fuel. And there are, cement production actually makes a measurable, it isn't huge, it's something like 3% addition of CO2 just to manufacture cement. And so that's one we don't think about that matters. Now this gets closer to what this class is all about. On the left-hand side are the sources of CO2. And of course the main thing on top there is burning fossil fuels. But the bottom one is deforestation and land degradation and disturbances. And so on the source side of our ledger of the carbon budget, we actually have a forestry issue of deforestation. Now, this thing doesn't show the arrows. There's supposed to be arrows going to the right. And basically, okay, so we emit all this CO2, about 37 gigatons, petagrams, units you've never heard of. And every year, what happens to them? Turns out that only about half of it stays in the atmosphere. This estimate is 44%. The other half, part of it goes into the ocean, and then that middle panel is the terrestrial biosphere. So on the one hand, forests are part of the problem, and on the other hand, forests are a big part of the solution. And this is what makes forest management conceivably pretty damn interesting in the coming decades, because they're both sides of the ledger of this really big policy deal for the world. And so this is a look, textbook style, of the overall global carbon budget, and on the left the big fossil fuel emissions and land use emissions, and then sinks for, as they call it, a sink from the ocean and a somewhat bigger sink from land. And then what's left is what grows in the atmosphere, and that's why the concentration keeps marching up in the atmosphere, is about half of it stays. All right, so given that this was a World Forestry Institute, I left out a whole bunch of climate slides, and I said, let's go talk about forests right now. And I thought for this class this would be most useful also. So let's do it. So let's first talk about carbon sinks and where they are worldwide. And this is a little bit of a fiddly graph, but you'll notice it's boreal, temperate, tropical forests, and it's from the 1990s and then a decade later. And it's basically looking at what do we see are the places that have the biggest sink. And what you see is the boreal forests are pretty small. They don't grow much, but there's a large land area. The temperate forests are a good bit bigger, but by far the biggest carbon sink is the tropical forests worldwide, and it appears that tropical deforestation has been measurable over that 2-decade period. Now, let's just skip that. This is just the mapping version of the same thing. So we know that where forest carbon sinks, where the forests are, where the big ones that grow the most are, this is generally known worldwide. Now this is kind of my one-slide picture of my career, starting in tree physiology and then working my way up to what I do now is write software for NASA satellites. And this software calculates global plant growth every day. And so this is the kind of data sets we build. And basically we first identify the forest cover types all over the world. And then we try to understand what controls their growth and stresses. And so this is a map we cooked up a decade or more ago, showing where forests are mostly temperature limited, where forests are mostly light and day length limited, which is of course the far north. They're just coming out of total darkness right about now for the year. And then where they're water limited, basically all the deserts and arid savannas. And so this is part of trying to calculate forest growth worldwide, is understanding what constrains and controls their growth. So a bit of kind of physiology. And so this, I don't think I'll talk us through this, but basically shows that you can take these really simple principles of what controls for tree growth, you can assign it to climate in the boreal forest of Russia and the savannas of Africa with real simple principles, and come up with dramatically different analyses of their annual growth. And if you're going to compute global forest growth, you got to be able to do this. So we've spent a whole decade building this kind of basic principles of how we do this. We calculate the growing season for the whole world. This is what that looks like, from the really shortest growing seasons at the way high boreal forests and up in the Himalayas. Of course, look at the Australian desert is a very short growing season because it's only when it rains. And so you could have a short growing season for a couple of different reasons, and this merges that all together. Well, to cut past a whole bunch of science theory, we run these calculations on this NASA data set for every day. We've been doing it since the year 2000, and this kind of gives you a look at what the U.S. looks like for a couple of different years. 2000 was a huge drought year, and you see that splotch, and then the very next year was dramatically milder, decent amount of rain in the south, no big droughts really much in the west, and the satellite maps all this. So this is really just an illustration of what we can do with satellite mapping of forest production now. Now when we look at the growth of the forest of the world, just as a final number of plant production, we've done this for 30 years, and you see that it looks like it might be going up a little bit. And so, but it certainly isn't going up very much. You'll notice the y-axis is going between 50 and 54 petagrams. So it might look like pretty steep slope, but it's actually only 1 petagram. So I wrote a paper in Science about 5 years ago suggesting, geez, maybe humanity actually can't. Given that we've been doing the Green Revolution for decades and all this, maybe we really can't enhance the global productivity. Maybe that's kind of a fixed constant. And if it is, it means that what is growing now, we've got to learn how to use, because we can't just make lots more. At a global scale, we just can't enhance productivity in any huge way. It might go up a slight amount, but this pie chart actually showed that there's only about a 10% of the global plant production remaining that isn't already actively used. 10% is all that's left. And so the argument here is that we really can't go find a new frontier and just find new resources the way we did 100 years ago, that we've got to manage what we have now to make it. And this gets to be kind of fiddly, but the climate models, simulations that you always read about in the paper, how it's going to be 3 degrees warmer in 100 years. You read this all the time, comes out of the global climate models. Well, one of the things we've detected is that they don't get the land plant production correct at all. They have, and so all these different lines are these different computer models, and they all show plant production going way up over the next century, and we say, well, over the last 30 years it hasn't. And so we're suspicious your models aren't really getting this part very correct at all. So this is the kind of stuff that some of our science falls into. All right, let's turn to the other side of the ledger, and because this is way more critical to us locally, and talk about forests as carbon sources. And of course, this is a crown fire going on. You can just tell at a glance. this is only about 20 miles from here, above Frenchtown, that we're up in the subalpine zone. You can see just from the forest height, and yet we have a crown fire going. It's interesting to look at the history of Lewis and Clark. When they came through here in 1805, and of course went over the hill at Lolo Pass, in 1806, they were so hot to get home that they just started out early, and they were in Lewiston, Idaho by June 21st. On June 21st, they tried to cross Lolo Pass, and there were still 20 feet deep snowdrifts. 20 feet on June 21st. And this is from their actual observations. This we know as hard numbers. Think about it now. Lolo Pass right now doesn't have 21 feet. By May 1st, it isn't going to have 2 feet. By June 21st, it will have been dry for weeks. And that's a perfect example of why our fire season is starting to rev up earlier, and it goes higher up into the mountains than it ever used to do. We used to have snowpack that, it doesn't burn in the snow, and so we'd never have high mountains burning because the snow didn't melt till the 1st of July. I remember I grew up in Seattle, and we'd want to go hiking on Mount Rainier. You didn't even dream about going before the 4th of July because you got the snow drifts. There'd still be snow patches, but at least the main drifts were gone so you could walk in the meadows. Well, nowadays, by the 1st of June, you can walk all over Mount Rainier. Well, one of the consequences of that then, we've publicized this for years now, is our fire season. And I suspect you guys all know a fair bit about our local fire season. And so this is where the carbon source part starts. Turns out that when they look at forests worldwide, there's a dramatic acceleration of what we call generally forest disturbances. It's different things in different forests in different parts of the world. For us, it's basically bugs and wildfire. For Algeria, who knows what it is. It's probably just pure drought in Algeria. But this huge paper came out in 2010 analyzing worldwide forest mortality from records in each country that just have permanent growth plots. We have permanent growth plots all over the forests. And so just analyzing these plot data, and they're just seeing a hell of an acceleration of forest disturbance and mortality worldwide. Now, this paper came out just about a month ago showing for the U.S., you look at, this is accelerating forest disturbance, and starting in the late 90s, you look at the plateau from 1985 to 1995, around a 2% disturbance rate, and that's now jumped to, this wants to scan our malware right now. Let's not do that right now. You see that's about doubled to about 4%, meaning about 4% of the forest area every year is disturbed in some significant way. Now, you take that 4% and just invert it, and you realize that means the entire forest ends up being disturbed, every 25 years? But that would come, that's pretty huge. So we're going to get back to this in a bit. Now, first from the climate point of view, and this is a computer model run, and the main thing, we kind of simulated the 1910 burn with this. We got climate data from back to 1900, and we basically said, what would happen if we just did a big clear cut, or, in the model it can't tell the difference between a clear cut and a fire. It just means all the trees went away. And what happens with any disturbance like this is, first, there's a big pulse of CO2 to the atmosphere. So when a forest is disturbed first, this big pulse goes out. Literally, it's just the CO2 from burning and the mortality. Then as the forest grows back, that pulse dampens down, and there comes a point in this simulation in about 20 years where the forest grows back enough, it starts becoming a sink again. And as it grows more and more and more, then it starts absorbing CO2 more than it's releasing. And so, as I said in the beginning, forests can be on both sides of the ledger. They can even be either be sources, particularly as they're burning, or they can be sinks as they're growing. And so this is what we have to try to work out worldwide. So one of the things we do with our satellite is monitor fire detection. This is a map for 8 days of fire in 2006 worldwide. One of the things that we've learned from this is that most of the damn fires worldwide are human caused. We're a funny part of the world where almost all of ours are lightning caused. But most of the rest of the world, most of that down in Africa and South America is purposeful burning, either for agricultural clearing or to just put in palm oil plantations or to get the trees out of the way for their cattle to graze. I mean, it's humans purposefully just torching trees. And that's something that I was surprised when I saw, because I'm so fixated on our forest, and to realize our forests are kind of the oddballs. This is a space shuttle picture of our fires that I've never seen quite anything like it. I find it kind of interesting. And so the second part kind of disturbance that matters to us around here, of course, is the beetle epidemic, and it started up in British Columbia. You can see that the bullseye of this epidemic. It actually kind of hopped over us and first went down into Colorado, and then kind of bounced back. And Montana was fairly late in this epidemic. It's gone on. They think it's pretty well run its course now, but it went on. You can see in this graph, it started in the late 90s, probably peaked overall around 2005, peaked here about 2010, and now we think it's slowing down, although I just talked to some Canadian forest scientists, and what they're scared shitless of is that it's going to jump from lodgepole pine to jack pine and then go all the way across Canada to the east. And they are starting to see signs that the beetles can do that. They've always thought those beetles were so species specific they couldn't make it in jack pine, and now they're saying shit, they can. So stay tuned. So we do satellite disturbance mapping too. And we talked about this 4% disturbance rate. Classically, the annual disturbance rate was more like 1%, if you just kind of took a big national and even global average. So, which means that a forest landscape would be disturbed about every 100 years. And that sounds more like what we've always felt around here. And so it seems like in at least a number of places that's gone from 100 years to 25. All right, because this World Forestry Institute's kind of a big policy player, I put in some policy stuff. When you talk about climate change policy, and they want to deal with that issue of deforestation, they call it REDD, in REDD+. And what that means is reducing emissions from deforestation and forest degradation. This lingo has been around for at least a decade, and that's what it refers to. And part of the big Paris Climate Agreement back in December actually had a REDD+ component to it. Now, it didn't make much headlines. If you weren't in forestry, you didn't pay any attention to it. But for people like us, this is the part of all that actually is our ballgame. And so I try to make sure that, of course, my students on campus know what it means and kind of know what it's about. And it's really to try to build policies so we don't just have this whole-scale deforestation that's contributing about 10% to global warming right now. It's not a small number. And it's just plain wasting trees is what kind of makes me mad. So much of it is just plain wasting trees. So you see some countries have put some serious money, $5 billion primarily to go to tropical countries. Nice to see Norway in there because I'm Norwegian by heritage. So the global scientists have followed deforestation rate and emissions for decades. And so this is a look since 1960 to the present in the CO2 emissions from forest degradation. You see that big spike in the late 90s where some of these Indonesian peat fires, those things are unbelievable.
I used to live over there.
You did?
Yeah, they were bad. They were bad. We call it haze season, smog season. I was in
Yeah.
Singapore. It was horrible. For 2 months out of every year, the haze comes over from Indonesia, and it's bad, if not worse, than the fire season here.
I guess they have to close down airports for weeks at a time. And I mean, it's worse than anything we've seen. And it covers a huge area compared to, we whine when the Missoula Valley kind of locks up. And this is a whole huge region. And so anyway, that spike showed in. You see that the emissions from forest have basically been going down since about 2000. So we like to think things are going better. But it's something that has to continue to be worked on because it's in all these different countries. So you have to really be negotiating with these countries to make it in their own self-interest to not be trashing their forests. This, let's not go through this. This was a quite detailed analysis of how managing tropical forests to stabilize CO2 could be done, and it gets pretty tedious. This is another look, though, from just about 2 months ago, that part of that Paris negotiation were for African countries to really start looking at restoring 100 million hectare of land. And, I've traveled all over the world, and we like to think that there's lots of big, pretty untouched wilderness area out there. I got bad news. There isn't. Everywhere, every corner of the damn world you go to, you just see humans have been trashing things left and right. And there's certainly a few small places, but when we think of this as the last best place, that is not much of an exaggeration. I've just seen stunning degradation, like Africa. Oh my God. And of course, all of Southeast Asia to me is overpopulated by about a factor of 5 to start with, and that then just is the preliminaries for the degradation. And so to at least get countries start to realize that we got to get to work, or we're just trashing the biosphere wall to wall, is damn important, because it's true, and we've got plenty of evidence to show it. So this is how we'd monitor by satellite. I don't think I'll waste our time here on that. One of the important things about REDD+ and carbon credits, one of the topics that's bubbled up over and over again is maybe we should start having carbon credits that can be traded and sold and things like that. The way they did with pollution credits for SO2. And quite successfully. They were able to drill down SO2 pollution about 5 times cheaper than the initial estimates were because of this trading mechanism that they established, where people that dropped their emissions lower than their target were allowed to sell those credits and actually make some money, which gave them incentive to really lower their emissions. This has been talked about for forests for a decade, But one of the fundamental problems has always been verification. Imagine that you're some big tycoon investor and you decide to buy the forest carbon credits in Cameroon for some zillion dollars. Don't you want to know next year that the forest is still there? And the next year, and the next year? And one of the things we know not to rely on is government statistics. They're bullshit. And so we now finally have, and this has only been in the last about 3 years, we now from Landsat satellite, which is a high, it's not a Google Earth resolution, it's 30 meters rather than 3 meters. But we can now process Landsat satellites globally every year and detect cover change. And this map is an illustration of how they do that. So this was a hell of a technical achievement, but it's actually a really big policy achievement, because this now means you could monitor anywhere on Earth that somebody might buy a forest carbon credit and see if after the country or the landowner took the money, if the trees are still there. So this is a huge step forward in this kind of policy. And so one of the points that I make, particularly in the forest management world now, and is that we've always had forest management for our regular, watershed and wildlife and timber production, the Forest Service sign sort of thing. We now have two brand new variables that forest managers never got any training in, and that are now real in our world, and these are the two, are either carbon credits or biofuels, as other possibilities that any piece of forest land a good landowner ought to at least be thinking about, along with timber production and wildlife habitat and those sort of things. We got two brand new variables in our equation. And so I've talked, and I don't think I'll go through this in detail yet either, because I kind of want to get to the biofuel part. Okay, and so first, so probably about a decade ago, the bioenergy topic started revving up. And particularly energy economists started making some estimates of how much bioenergy could be produced. And of course their whole objective was, gee, could we quit burning fossil fuels and basically make ethanol and out of biomass and eliminate all the fossil fuels. And so the dotted line in this graph is the current global energy consumption, all energy, heating, cooling, transportation. This is the whole energy, and the units are exajoules. And so we're burning about 500 exajoules a year of energy. I shouldn't say burning, this is all energy, so including hydro and nuclear and all that. Well, the papers there on that left-hand bar are all these different papers that were written proposing bioenergy contributions to future global energy. And some of them down there in the bottom were pretty reasonable, but others were stretching up that high range to 800, 1,000. I mean, the most ridiculous one, 1,500 exajoules. That's triple the amount of energy the world uses right now. Well, this Smeets paper said, we think bioenergy can deliver 1,500 exajoules per year. Well, that's about the time I started saying, wait a minute. Don't I have a data set that calculates global yearly plant production? What if I just assumed that we took all the global plant production and by magic made it biofuel? How much would it add up to? And so basically we did a little side project. We never did get any funding for this. We just did it on our nose. And we computed first what if we turned the whole world's plant growth into biofuel every year. So you basically clear cut the planet every year, and whatever grows back, you clear cut that next year. And now just what is this kind of lunatic capacity? And but we first made a couple of subtractions from the available pool, and one of them was all the food we ate. And so we took out everything that is part of human food production. Second, we took out all the land area where the growth is so small that it takes you more energy to harvest than you get back. That turns out to be a whole bunch of like eastern Montana. Out it goes. Yeah, it grows a bit, but it would take you more energy to go get it than it would ever pay off. And that turns out to be all sorts of East Asia, just all the arid savannas of the whole world. I think that took out 20 million square kilometers with that one assumption, which we think is a very realistic one. Anyway, to get to the bottom line, we finally determined that the most we can imagine bioenergy can contribute is about 100 to, at most, just impossible most, 200 exajoules. And none of this 1,500, not even 500. And even 200 would be unbelievable. So to us, a working number is 100 exajoules. Now that isn't chump change. That's still 20% of global energy right now. But what the point we tried to make with this paper is that these damn economists have got to quit assuming that the whole world grows redwood trees, because that's kind of how they got those monster numbers. Just imagine redwoods growing everywhere that they could go get. And so
Does that number change if you change the biofuel crops though?
it only changes a little bit. It only changes a little bit because, and you know, this is kind of global scale theory. This is, but it doesn't matter what you plant up in Fairbanks. It ain't going to do a whole lot. And that's the whole point, is we start with those global climate constraints. And if it doesn't rain enough, if it's freezing cold, I don't give a shit what you plant. It ain't going to do much. So you can improve some in some places. So as you drill down into real world decisions on a certain plot, you could do better. But we can't imagine that will magically, double the amount of overall bioenergy. It just doesn't add up. So now we're hoping that these sort of scenarios, pushing out renewable energy from now till 2050, and of course drilling down on coal particularly, and gas and oil, and wedging out solar, wind, and then of course there's our biomass wedge. We hope it's just a realistic number. I'm actually, I wouldn't have bothered coming over here today, but I'm hoping bioenergy can be a helpful part of this. But we got to be realistic about it and not be using moonbeam numbers. And so we wrote about 3 papers on this. They got a fair bit of notoriety, and we like to hope that they're in the main journals, that anybody that tries to publish these moonbeam estimates can be shot down with one reference to our papers. Because our papers are based on our satellite measure of plant growth worldwide. They aren't just made up. All right, so now it's on to bioenergy, which is what you guys were here for to begin with. And I remember back when there were slash piles like this in western forests. I grew up in Seattle, and they had a preferred species, and they just considered the rest junk, and they would burn slash just, oh my God. And of course we've done fairly much the same thing in the last 10 years here, cleaning up beetle-killed lodgepole pine. Did you guys see some of those piles up at Georgetown Lake? They were epic. They were the size of this building, and better. I was never around when they torched them. which is probably good, because it just kills me to see the waste of that much biomass. To realize that we can't do anything more clever than to just torch it into the sky. And so I guess that's where I see the role of, the most legitimate role of biomass in forestry is to find out how we can use effectively any dead forest proactively rather than just burn it up in the slash pile or let it stand there. Now in the parks we'll let it stand there. So, but for all the rest of our landscape, let's see if we can find something useful to do with it. And to me that's the bottom line for our forest bioenergy. I'm not very enthusiastic about the real kind of Weyerhaeuser high yield forestry sort of attack on bioenergy. You tend to put more energy into accelerating the growth, particularly when you start fertilizing, and certainly if you start irrigating. You basically spend so much energy managing the forest that you basically lose whatever, particularly carbon balance benefit that you would have gained. And so to me, looking mostly at natural forests and mostly that have, by this accelerating disturbance, are being killed is where we should really start.
As that 4% number grows, we're just going to have more residues to work with.
And it might. And one of the questions though, that I think if you buy that first premise, that we should go after dead trees first before we go and start any active accelerated management, which in the southeast might be a little more worth it, but for the whole northern Rockies, I think is a pretty functional assumption. One of the things that I'm becoming more and more convinced about is trying to make ethanols the wrong thing to do. And I'll bet you guys are probably going through this a lot in this class. And I just read paper after paper. This was a big, this was a paper that illustrated all the losses on top, starting with the unit of biomass. It almost doesn't matter what, and trying to work through the organic chemistry to end up with ethanol. You get about a 10% final efficiency. Whereas if you simply take that biomass and burn it for electric power, you get more, at least double that efficiency straight out of the chute, and even better. And so to me, that tells me, especially as we're waking up to electric cars, that the battle to make ethanol was primarily to put in piston engines. I think piston engines aren't going to make it another decade. In fact, I don't intend to ever buy another piston engine car. I've got 2 cars that are new enough now that by the time I replace it, I expect it to be electric. I mean, imagine doubling the efficiency by simply taking out the piston engine and putting in an electric motor, and the whole rest of the car is identical.
And then you're harvesting the forestry residue with electric equipment, it's like,
Yeah.
you just repeat that and increase your efficiency.
Yeah. And so to me, this makes our job easier, because instead of beating our brains out on the organic chemistry of like cracking lignin to ethanol, which they've been beating their brains out for 20 years on, we just say, well, screw that. And we go straight to taking our biomass and finding how we can burn it most efficiently. The wood generator we were going to try to get on campus here was going to be a cogen, which I read over and over again is, of course, first you want to burn the driest, you got to be able to dry your material first and then chop it up in ways you guys probably know all about better than I do, and then have it in a high temperature combustion chamber. And then running like a steam powered electric generator. But then you've got to be able to use the waste heat for something useful. Seems to be a really critical part of making the whole shebang worth it. And that means primarily space heating and water heating. It becomes a real interesting systems problem, because instead of just worrying about the biomass and burning it well, you actually have to put the whole puzzle together for it to work. And I think this is where the bioenergy world has to get smarter and smarter, is they have to start taking on more of the overall issue rather than just staying narrowly in their own domain. And that's what we all like to do, because that's what we know and we're good at and feel competent. But we're just not going to win on this one if we don't. And it's particularly with natural gas being so cheap. We can't just compete toe-to-toe on raw dollars. We have to be factoring in, the cleanup of the dead trees and the forest fire vulnerability aspect of this. And, the forest carbon sink of a cleaned up forest regrowing again. We got to put all those pieces together. Then I think the bottom line pencils out. But if all we do is say biomass takes, 5 cents a kilowatt hour and natural gas takes 3, we lose, we go home, then we're going to keep losing and going home, which to me is kind of what's going on right now. And so I really find that that's a key part of this. Now, turns out this exact place is, did any of you have anything to do with this? Okay. Yeah, so you guys know more about this than I do. Not making any statements about how good this exact unit was, this is the right idea. Is take your generator to the woods. Everything falls apart when you have logging trucks driving 100 miles. And so I only saw this once. Is it still around town?
It is. It's down in Corvallis right now. Brian Jackson's running it.
Okay.
It's a greenhouse, using biomass out of the greenhouse.
Oh, good. This is the kind of idea that we have to keep talking about and figuring out how to put the whole system together for this to work. Because I think that's how we can solve the forest disturbance cleanup part, the direct electric power production part, tied to a greenhouse so the waste heat becomes just greenhouse heating is perfect. That's, I'm sure, what they're doing. I go over to the rec center. In fact, I'll go when I'm done here, and I sit there taking my shower, and I think of all the other people taking hot showers, and I think, boy, I wish this hot water heat was coming off of biomass. And it would have been if we could have sold that wood plant. Now, Brad and I worked politically, I guess, as much as anything, for the new building to get one of those. And I guess they wouldn't quite put it in, but they stubbed in all the connectors so they could at a future date, is what I've been told. Because I still think when the right situation comes up, and of course the right situation can be nothing more than tripling natural gas prices, which is going to happen in the next 5 years. Now that they've quit drilling, the boom went bust, and the bust is in full bust right now, and then they'll run short, and up will come again, and the same old shit. It really pisses me off, because it's so contrived and artificial. But that's all it would take, and suddenly these bioenergy ideas would be way more viable. And so I hope you guys are over here furiously cooking up next generations of this. And Brad, he's put me on a number of his proposals, so I can, from kind of a global climate and carbon theory point of view, help argue the case, just like I'm doing with you guys here. Because I think we're only one big grant away from getting to do a full test bed, next generation test bed of either this. Have you guys had anything to do with that green wigwam up in Columbia Falls that just burnt down? You know what I'm referring to?
I know, but I don't.
Yeah. It burnt down about a year ago. I guess they got insurance money, and I read about 5 months ago they're rebuilding, which I was wondering if they were just going to abandon it. But that is another sort of full system biofuel, bioenergy idea that's around, that you start by burning the biomass. You use it to heat a greenhouse, to heat an aquaponic system. You produce electric power first. You then use the residual heat to heat the greenhouse. And then you have all this aquaponics and then biochar production, and there are like 5 different things going on. But I think that's what it takes. No one of these factors can ever pencil out on its own, is what I'm convinced. And you got to make the whole system argument in order to win. And that's what I hope one of these days we're going to win and get something around Missoula that can show this. So this is just more diagrams on biofuel versus wood products. You guys probably know all that way better than I do. The current market value of 2x4s versus bioenergy. Bioenergy is really just competing for the hog fuel market, effectively, for the bottom end stuff. Anything that you can still make structural lumber is always higher value. Isn't that true? Yeah. And yet that's fine. There's plenty of residue to work with, and especially with accelerating disturbance. We need to just plan on that, because we see in the data that it's already well underway. And so we get in. This is something I wish our College of Forestry would really get in the middle of. And hell, I'm a professor there, and I can't even get. Our best 2 faculty on this just moved to Oregon State. And it just isn't something. The carbon accounting is what I'm referring to, getting very accurate carbon accounting. If we do this, we get one carbon budget. If we do that, we get another carbon budget. Optimizing which is the best. It's a tricky bit of carbon cycle science, economics, and policy all put together that we ought to be good at, and yet we aren't at the moment. Other universities are, but we're not one of them. And because this is, I think, the bottom line of forest management decision making in the future. And so these are slides from a guy up in the Canadian Forest Service, and they're way ahead of us. And so part of what they really look into hard, one of my old students works for them now, is the decision making between, well, should we harvest at about the schedule we used to for our regular 2x4s and plywood and wood products? Should we let them grow an extra 20, 30 years, assuming that the carbon sink is valuable enough that beyond the typical economic calculation it's worth it? One of the things I'm starting to watch a lot is they now have a new technology for being kind of like super glue lambs, that they now figure they can build 15-story skyscrapers out of wood. Finland has built a couple of these, so this is not vaporware. I think Vienna is building one. Portland has 2 of these buildings on the design block, and they're really seeing this as maybe a potential for the wood products world to basically swipe some of the lunch of the steel and concrete construction world in the future. That's absolutely what they're after. They think if they can prove that wood can do the job, and that its carbon footprint is way smaller, and that it helps with these other aspects of forest management, can they make that a winner? And at least for certain of you look at every building in Missoula is shorter than what they say now the capacity of these things at. So in theory, every building could be wood if they choose to. I don't know, I'm not in forest engineering or econ, but it's certainly something that would be worth watching because it seems to be getting some momentum. It seems to have gotten past some of the building code restrictions that have always limited wood structures to, I think, 3 stories right now. And so now I know this one in Portland is supposed to be 10. So anyway, that's another part of using our forests, and especially our dead forests, a little more valuably than we have been. And so, yeah, this is for this World Forestry Group. This was kind of my grand finale, so to speak, of could we think up a way to not only slow down deforestation rates, but more effectively use the forest we have in bioenergy in a much more comprehensive way, and possibly in construction engineering in a new way. And of course for them, I reminded them of these future climate projections that if we don't do anything as a society and decisions, we end up at that very top of that graph at 2100, and with a planet that is definitely frying, no two ways about it. Or can we drill our way down to some of those lower and lower trajectories, and forest bioenergy is part of the solution. And then I showed him about this global carbon budget paper where all these numbers came from, and gave him a little pep talk on the climate change minor. And and then I like using this. This is the most distant picture of Earth ever taken, 1 billion kilometers away. And I guess if somebody goes and sees the movie The Martian, they'll realize we can't just bail out to Mars if we wreck this place. So that's the way I like to end these things. There's not a lot there. So that was the World Forestry talk, but that particularly for you guys is a little extra thinking on bioenergy and biomass, and I hope we can argue one of these cogen plants for the new building. And I hope they really did stub out the connections that they said they had. Brad and I, for 2 or 3 years, have been talking around. I know he's been submitting proposals. He does that part, but I've been...
I will tell you that pretty much, as far as that, getting a line to be able to put in one of those cogen plants is easy enough to do, even if they didn't put it in. But overall, we ran into a lot of resistance across the board. One of the things we asked for was a geothermal loop. Because they're digging up the ground anyhow.
Yeah.
We're literally talking $1,000 to bury a good size geothermal bed out there, and they wouldn't even entertain that.
Shit.
So,
no kidding.
they would not allow the wind turbine to go back. Well, they would if we put it behind the building. Which
First
is kind
out,
of
wind turbine. Missoula's not a wind turbine joint.
It's
so-
not, but actually that
Yeah.
one was fairly successful. That is probably the only location.
You're right. If you are going to put one here, then Hellgate Canyon is the
It
place.
turns out it's going back up this spring
Yeah.
over in Bonner.
No
The
good.
new Kettle House Brewery. is going
Oh,
back.
is Kettle House going out to Bonner?
Yeah, they're building a new building out there
Jeez, I'm the last to
by the
know.
mill.
Yeah, right with
Oh, okay.
Yeah, on the river. It's gonna be nice.
Yeah, it's gonna be sweet. Same way with the solar, our solar arrays we took down from the hydrogen plant are not
Yeah.
going back up there.
Yeah.
So,
They're probably old enough there. They weren't very up to today's capacity anyway, were they?
yeah, they were.
Were they?
One was
Were they?
only 6 years old.
Oh, okay. That wasn't too bad.
So, we're looking at it more for every little bit helps, but we're looking at it more from an educational
Exactly.
standpoint.
Yeah.
And, this one's gonna have solar on the roof, but we're not gonna have access to the roof to be able to work with it. So,
Yeah, to actually be able, see, I would like to be able to take students up there and be able have them do measurements, like different times a day, for example, different sun angles, how much you lose,
Right.
and things like that. And it ought to be an educational part of that they called it, they had a funny name for that thing up in Columbia Falls. And I don't in any way want to promote their particular facility, but their concept of a unit doing like 5 different things was very cool.
A good example for that, if you ever checked it out yet as well, Wood Brewing down in Stevensville.
Okay,
Just before the turn to Stevensville there.
okay,
They're looking at a carbon neutral system, and they're
Yeah.
very close, they're not quite there yet.
yeah,
But like there's CO2 coming off of the fermentation process.
Yep.
Their greenhouse that grows hops is attached to the
Good.
brewery. So
Good.
the CO2 is pumped right into the for the
Yeah.
hops plants too.
Are they in any way having, or would they allow students to come take measurements?
Oh, yeah. They can
Because,
take tours.
you know, these things, you put this stuff up, but it takes work and time to actually monitor it scientifically. And I don't blame them for not having the time, but if they'd allow us, our students, to go down there, that would be huge, because then you could get real numbers of how well something like that's working, whether there's components that turn out to not actually be worth it after all, which then everybody else can learn from. And I applaud all these businesses that try this stuff, but I sure wish they would also let us deploy students for some monitoring of efficiency, because then everybody learns for the next and the next and the next. And that thing up in Columbia Falls, I know I had them for one of Brad's proposals. I had them estimate how many student employees that they figured they could use for all the different aspects of operating it. And it came out to something like 20. And this is just for a pretty small scale unit. And I thought about it again more as an educational facility where these students would be measuring how good each of these steps is functioning, how efficient the steps of production are in energy, in heat, in the greenhouse vegetables, in the aquaponics. Taken measurements of how, yes, this is a great theory, yes, it's a great idea. Let's see how well it's actually working so we can learn something, so that the next generation continues to just get improved and improved. Because otherwise that doesn't really happen if you don't have hard numbers.
And a lot of times they won't let you measure that performance because it's not what their claimed performance is.
Yeah.
And they don't want that
Yeah.
publicized.
Yeah.
That carries them to
Yeah.
a certain extent.
Yeah, and I understand from a business point of view that, yeah, if this is part of their marketing, which, you know, I love these companies that are giving this a try, but you hope that if you could get them to realize that none of us learn anything for improvements without careful monitoring. And hopefully at least some of them will buy into that. And having one right on our own campus is, of course, the best of all, because then you don't have that compromise, and you have all these students just sitting waiting for some hands-on learning that you can deploy. So, okay, well, that's all I know on these topics. And
The only thing I want to bring up, Steve, on that, the ethanol version
Yeah.
there. The other thing is really critical to understand in ethanol production, that they, in the same way you took the numbers, you said their climate models are wrong because they expect this exponential growth.
yeah,
It doesn't happen. They do the same thing with ethanol. They equate 1 gallon of ethanol to being 1 gallon of gasoline.
Yeah.
It's not
Yeah.
even close.
yeah, it's something like, what,
70%?
77%
Yeah.
of a gasoline, yeah.
So the
Yeah.
numbers kind of, you know, and you talked at best, you have a 10% margin. you know, that you're
Yeah.
dealing with. Well, if you start figuring it at 77%,
Yeah.
there goes your.
Yeah,
there goes
whatever
your-
little margin you thought. Yeah, I'm just down on ethanol entirely. And I've read that very carefully for a half dozen years. I'm not making this as just an idle conclusion. And every different which way I think of it, I just see the route to effective use through electricity being so much more direct, with so many fewer pitfalls and so many more opportunities. Boy, once you have electricity, you can use it in so many different ways.
You know, there's just so many industries that are so invested in piping, trucking,
Yep.
and pumping, you know?
Yep.
It's like that's the motivation behind it.
Yep.
That's it, you know?
Yeah.
Get off
And
that
subsidies.
infrastructure. And subsidies.
Yep.
Good.
But the efficiency of burning it to generate that electricity, to generate heat and everything, especially at the commercial level, you know, if you're burning it in your wood stove at home, that's probably not the best use of it.
Yeah,
But if you're burning it at something that has a, you know, 87% efficiency rate, using a gasification system,
Yep.
fluid bed boiler,
yep.
now all of a sudden, it's pretty attractive.
High temperatures, putting off
Yep.
steam and.
You know, I think the UM kind of blew it when they proposed this, that they did not effectively make that argument, that this isn't just a giant wood stove.
Right.
Which is, I think a lot of the pushback was assuming, is that it would be just kind of a giant wood stove, and they don't understand burning at 2,000 degrees instead of 5